Today's talk is entitled Knowledge Processing, Logic and the Future of AI. It will not be a very technical talk, but we will have a few technicalities, let's say, but it will be maybe a little bit mixed between philosophical, historical, and technical considerations. Okay, and I will talk also, as part of this talk, I will mention my recent project, which has started just very recently, which is called the RAISON Data project. And you see AI here is part of RAISON Data, okay? And this is funded by the Royal Society, and it's a 5 years project. We have basically done half a year, done some initial research on it, and it will continue for 4.5 more years, hopefully. Okay, let me give you my view of how of the developments of AI from its beginnings. Of course, I'm not a historian, and what I will tell you now is extremely condensed. So I know that there are, many ramifications that I cannot tell about in one single slide here. But we have basically in AI, we have two big columns. One is the symbolic AI column, and one is the subsymbolic column. And both of these columns have developed in parallel. Yeah, and basically they were here at the beginning of computer science. They grew with the beginning of computer science. Now, certainly symbolic AI, we know, has its much deeper roots than subsymbolic AI. It rests on thousands of years of experience and of work in logic with a lot of famous people, Aristotle, Avicenna, etc., Tarski, and so many people, Moshe Vardi, for instance. Dana Scott is already here, Dan Scottus, but a lot of people have worked on this. The real birth of AI, of let's say symbolic AI, is 1956. By the way, that's my own birth here, I have to say. So I'm as old as AI is. By John McCarthy, that's when people say birth of AI. Yeah, normally they'd say that's done in the year, that was the year 56 with John McCarthy. And John McCarthy said, as one of the important, and there were others, Newell, Simon, Shaw, they came up with a system already in this year, which was called theorist, okay, which was a kind of theory proving and system, rule-based theory proving system. Now, what is important here for logicians is actually that McCarthy said AI needs knowledge representation, KR, via logic. Logic is essential to AI. So that was one very important statement of McCarthy. And then came a big important period with expert systems. Expert systems are systems, and I think that was a very important attempt, and partially only successful, unfortunately, an attempt to capture common sense logic with rules, but not only common sense logic, but they started actually with very specialized logic in certain domains, medical domains and engineering domains, etc. And then in the next, sometime later, there was expressive and efficient logics were used to work with big data. And we have a lot database theory, relational database theory is based on logic, but more recently also ontological reasoning, description logics, variants of a language, which we will see in this talk called Datalog, probabilistic reasoning, Markov logic are very new logics that have been developed for artificial intelligence, basically. Okay. On the other hand, the other big column, and the interesting thing is that until recently, these columns were completely separated. Yeah, the other column is the subsymbolic AI. And subsymbolic AI means basically the AI of neural networks. And this started actually earlier, but of course, what does it mean earlier? Because logic started so early, but the beginning of what we now call subsymbolic AI, what was not called AI then, yeah, was in around 43 with McCullough and Pitts, who modeled simple neural networks by electrical circuits at that time, not by programs, yeah, by real electrical circuits. And 1958, Marvin Minsky developed the basic theory of machine learning, actually. And actually, he already had some ideas of what now is known under reinforcement learning. Then another very big step in '86 by Rammelhardt, Hinton, and Williams was backpropagation. That was the basic for very fast and efficient neural networks. And currently, as we have to say, so maybe I should also mention first, there was an AI winter. Yeah, there were many years where AI was seen as a pariah of computer science, where people looked down to AI, and they looked down to both columns of AI. They said expert system is not worth it. So, and they said neural networks are even less work than expert systems. That was the general tendency. This tendency was partially understandable because people were boosting, and they're always boosting in AI. It seems to be something that connected to AI, that people are always boosting and asking for lots of money. Okay, and then they don't deliver as much. Okay, they deliver, but they don't deliver probably as much as they promised. Yeah, and so people, generally AI was, people say the AI is out, okay, from approximately 85 to 92. Now, I'm not a historian, and other people say there were actually 2 AI winters, etc., but we don't want to take it so precisely. But let me say that now, currently, machine learning, neural network-based machine learning is a huge success. Everybody speaks about it, and actually people are identifying AI with it. Yeah, so since 2012, there's an incredible hype in machine learning, mostly justified because machine learning can do a lot of very, very good things. And people are really questioning whether most people to whom you say AI now, they just think it's machine learning and nothing else, okay? And of course, there are great successes and there are greater and greater expectations. And people are now starting to fear that the expectations are a little bit too big. Yeah, people expect completely autonomously driving cars that are just based on neural networks, etc. So, and if that fails, then unfortunately the logical part of AI, will also suffer from it. So we are unfortunately prisoners of all this. Yeah. So the interesting thing is that both types of AI were suffering very much, and both were disregarded for a while. And now Subsymbolic AI is the big winner for the moment. And I will address this a little bit in this talk. Okay. So what can machine learning really do well? What does machine learning do really well? Machine learning does well pattern recognition and classification. Yeah, image recognition. That's where machine learning is super fantastic. Okay. This is actually what also animals and babies can do. A baby can recognize its mother with nobody telling the baby, your mother has brown hair and your mother has a small nose and your mother has glasses or doesn't wear glasses, etc. A baby recognizes its mother through positive and negative rewards, and probably through a very similar mechanism. I say probably because I can't look into the brain and nobody knows it, but it looks from the outside, let's say the behavior is just similar to an artificial neural network. And this is a human neural network, okay, an animal neural network. Now, animals do the similar way recognize their mother. The mother gives the baby good things, food, attention, caresses, whatever. Other people don't do that in this way, and so the baby learns to distinguish the mother from other people. So this synchronicity of good things coming with this picture, with the image of the mother. Okay. Then again, what neural machine learning is doing very well is reinforcement learning, in particular, to explore an environment, to try out things. This boy has touched a nettle, and you see he's almost crying, maybe crying, or at least shocked by touching the nettle. Yeah, and he won't do it. He will do it maybe one other time to make sure that this always happens, but 2 times would be sufficient. And until the age of maybe 13, he won't do it. With 13, he will do it to show how brave he is, etc. to his career. But from maybe 5 to 13, he will not touch a nettle. Okay, and this is also a learning effect. And this is very similar to what is reinforcement learning. You try to explore the space. And here's another example. A baby learns without anybody telling the baby. Nobody has to tell the baby you cannot go through solid matter. Yeah, you cannot transpass solid matter. You have to stop. Yeah, and this is the situation where the baby learns it. Yeah, it hits its head, or maybe its hand, or whatever. I mean, it doesn't have to be so painful, but avoiding obstacles is something that babies learn, and that computers and hoovers, yeah, robot hoovers can learn, yeah, automatically. But babies learn that completely from themselves. Nobody has to tell a baby. Baby doesn't even speak at this stage. Okay. Now we come to a counter argument. Now people tell me, yeah, but computers can also play chess, and computers can also play Go, which is even more difficult than chess. This is true. But what I claim is that actually the same mechanism, even though with many more data that the baby could never have and incorporate, yeah, a similar mechanism happens here. Yeah. What is the big success in, for instance, in the best Go program, AlphaZero is currently, as far as I'm up to date, is a world leader in Go playing. It's simple tree search methods, but the most important thing is to recognize a situation. And it's again a kind of pattern recognition. Is this a winning or a losing situation? Yeah. Now, it's not only this, it's already a little combination of this with a few rules and a few other techniques. But essentially, the computer learns by seeing millions of positions, by playing against itself. It learns, yeah, which is a losing and which is a, to very quickly classify positions and to cut off, yeah, this search tree enormously, so that at the end you find a good solution. Okay. Now so now we have said what machine learning can do really well. Now let's see what machine learning cannot do well. Let's say, I say cannot do is maybe wrong, but cannot do well. And here's an example. So you see here an image that is not very clear because it was taken through a computer camera. And that was a real case reported by the Telegraph. It's a newspaper that I usually don't read, but it was, in this case, it was an interesting article on the 25th of November, 2018. There was a bus crossing a street, and the street there was a red light here for, people had to wait. And then on this bus, there was an ad with this lady. This lady is a famous person, very well-known person, I think a businesswoman, a Chinese businesswoman, and her face was on the bus, okay? And then she got a ticket for jaywalking. So you can see machine learning recognized the picture and probably recognized her and then matched this picture against known picture with the name, and then recognized her name and maybe her passport picture or so, and then wrote a message to the police and said this woman was jaywalking. And actually, she was only on the bus. A human, of course, would recognize this, but this is not such a situation. It's not a situation that you can learn so easily. Yeah, it's a situation. It's a rare situation, pretty rare situation. And machine learning, I mean, normally you don't have that even in the data, such cases. Yeah, for machine to learn. Okay, but a human with common sense knowledge, even a child, will recognize that immediately, because a person knows, well, if you cross the street, you need to have a full body, you cannot have a half body. If there's a bus, that this bus is an obstacle, so you cannot cross the street. But next piece of common sense knowledge, on buses there are ads usually, and on ads there are sometimes people. So if you put all that together, yeah, we do that. Yeah, so we recognize a picture, we do some neural processing, but at the same time, we superimpose common sense knowledge, and then we conclude, oh, this is an ad on a bus. Yeah, maybe we also can recognize that this is an ad of the bus, but I think in this situation, we do something more than just a pattern recognition. Yeah, there is some little, I think, I cannot prove it, of course. Yeah. Anyway, machine learning can't do that very well, and the proof of this is that this woman was fined, yeah, because she was jaywalking. Okay. Here's another very famous example that several of you may already have seen. This is an example by Google, actually. It was presented at NIPS 2017. You can cheat pattern recognition systems easily, okay? And here's the way to cheat them, which is quite interesting. So here you see a banana, and here you have a classifier, and have several possible outcomes: snail, slug, banana, orange, etc. And you see there's a slight possibility this is a slug. So here you see a kind of probability, that the system attributes to it. And banana is of course very high, and that's correct. Yeah. And now you place a sticker, this sticker here. Yeah, you place this sticker, which is a very strange sticker, which they called psychedelic sticker. Okay, they placed this sticker here. Yeah, and suddenly this was no longer recognized as a banana, and the sticker had a tiny toaster on it. Okay, so suddenly this was not recognized as a banana, that was recognized now as a toaster, highly, and only with a very low probability as a banana. Yeah, and then they made a lot of experiments, and with such stickers you can really fool AI incredibly. So you can put it on a traffic sign, and that's actually dangerous, I have to say. Yeah, if they are automated drivers, etc. Yeah. You can fool people. You put stickers of this type on a traffic sign. What is interesting for me to see is that this sticker is a very attention-attracting sticker. Yeah, it has many colors and is like really something that flashy, that even a person would be draw its attention to this. But maybe that has nothing to do with the machine learning algorithm. I don't know. But what is really interesting is also, well, a human recognizes, well, a human would immediately recognize this is still as a banana and would say, well, this is a picture of, in the best case, a picture of a toaster with something else, but this cannot be a toaster, simply because we could have knowledge that could be in some knowledge bases, but did we know, well, a banana is usually, in most cases, larger than a toaster. A toaster is larger than a banana, and the banana is smaller than a toaster usually. Yeah? So it cannot be that there's such a microscopic toaster. You couldn't toast a bread with it. What do you use a toaster for? You use a toaster you toast a sandwich. A sandwich has a certain size, similar, maybe half of a banana, but not, yeah? So it's impossible to think that this is a toaster, okay? But of course, even a human has to think a little bit, what is this? Yeah, but he or she would be immediately recognize a banana here. Okay. Now we come to more critical things. Yeah. This is about credit scoring. Jamie Heinemeier Hansen had a better credit score. That's a very well-known case, actually. You may have read it in the papers. Jamie Heinemeier Hansen had a better credit score than her husband, who is a tech entrepreneur, David Hansen. They have equal shares in their property and file joint tax returns. They earn the same amount of money. Yeah, yet David was given permission to borrow 20 times the amount of his Apple card than his wife was granted. Okay. Now, so they said there must be some gender discrimination here. Okay. But Apple said no, gender is not even an input to our algorithm. Well, but Rachel Thomas from Data Ethics said, well, even if race and gender are not inputs to an algorithm, the algorithm can still be biased because it has some typical attributes and so on. Okay, so it's not that you have to have it explicitly, this gender in, and as long as you don't have gender, everything works well, and you can give a much lower credit rating to a woman. Yeah, so there's also something here to recognize. Yeah, next. My own example. Yeah, that's my favorite example because I suffered from it. I lived it. My own credit rating. So I own several credit cards. Here I show you 9 of it. This one I have changed the name because I don't want to be sued by this bank. This talk is recorded. So so what happened? I had all these credit cards, and I have a usual credit limit of 20,000, 8,000, 10,000, 10,000, 8,000, 12,000, and then 14,000 on these other cards, okay? And I really wanted this card because it has a very good exchange rate and other good properties. Yeah, it's a very good card for international traveling. And they only gave me 500. So I was really angry and upset. And I called this bank, Cent Bank, and they told me, well, you know, we don't do it. A credit rating agency does it. And so give me the number, please. You have to, because there's an obligation to explain things. So please give me the number. And then finally, they gave me the number of the credit rating agency, and I called the credit rating agency, and they told me, well, we have the best machine learning program. So this is This is it. I mean, machine learning determines that you only have to have a maximum 500 credit limit. We already gave you the maximum. So I was very angry and said that I need to know more about this. This is not an explanation that you have a machine learning program. Yeah, but it's complicated. We don't know. Please try it. And so they promised me after 14 days that I could call them back, and I did. And they say, well, we still don't understand what this really is, but it must have to do with where you live, okay? With the house where you live in. So immediately understood what it was, because I had bought a new house where I moved in with my family. But before we bought the house, I was visiting the house in Oxford. And there was a gentleman in who was the tenant of the previous owner, okay? And it was a nice guy, but he looked already a little bit strange to me and so on. Too nice, maybe, yeah, too nice, nicely behaving and so too friendly. And as soon as I moved into the house, every day I got tons of unpaid bills by this gentleman. Yeah, and later on, this guy was involved in a big scandal in Iceland. So I read in the newspaper about him. Yeah, but so I got unpaid bills, and people were ringing at the door as this guy is owing us money. Yeah. So then I understood clearly understood what has happened. Machine learning has learned the following reasonable rule. Reasonable under, I will tell you, it's not really reasonable because it's unethical, but it's reasonable in technical terms. People who live in a joint household with somebody who does not pay their bills are likely to fail repaying their own debts. Okay, so it has learned a statistically true rule, probably. Yeah, most people who live in a household, yeah, you know, with somebody, yeah, they live, probably they are either couple or brothers or sisters or siblings. Yeah, so likely that both, yeah, if one cannot pay their bills, then the other one cannot pay, because yeah, otherwise, yeah, maybe they would borrow each other money, yeah, lend each other money or borrow from each other money. So this ethically, of course, very questionable rule, yeah. But it was statistically, I would say it's a correct rule, was applied to completely wrong data. Why to wrong data? Because this guy was no longer living there in the house. Yeah, but of course, in their database, the rule was still there, because in England, you don't have to go to anybody and say I don't live there. Yeah, and you can, of course, at some point you have to tell the tax office that you don't want to pay council tax, you don't want to pay local tax, as it's called in the States. Yeah, but that takes a year or half a year until this migrates possibly, and not even surely, into a database accessible to the credit rating agency. Yeah. Now, human credit raters know this. They know, well, my database is certainly not perfect. And what they know is, if a property owner moves into their if property owners move into their recently bought one family property, then with high probability, the previous occupiers have moved out. Okay, so that's how we reason. You bought this house and you moved in. I would never think that I'm responsible for the debts of somebody who used to live there before I bought the house. Okay, but machine learning doesn't know these rules. This is a typical rule that I would, if I was to construct a system, an automatic system for credit rating, I would interview seasoned credit rating experts, and I would take these rules in addition to machine learned rules. And so this rule would invalidate, this rule would actually this rule would let me, let's say, execute an action on the data, on the machine learning, on the data to be subjected to machine learning, namely that this guy still lives there. I would put maybe 0.1 probability or less than 0.1 probability to the fact that this guy lives there, because that's common sense knowledge. If somebody moves into a house, yeah, that the previous tenant doesn't live there. In some very few exceptional cases, this is the case. If I buy the house of my auntie and I let her live there, then we all both live there together. But that's very rare, and that's why I don't put it 0. Okay. But from a risk assessment, from a risk perspective, and that's what these credit rating institutes do, yeah, agencies do. Yeah, from a risk perspective, this is can almost be neglected. Okay, so this is why I think that this is an example where I think that common sense knowledge is better, and you cannot learn all these things, all these exceptional cases on this specific. I mean, you can learn them maybe, but then you would take it. You need such an enormous amount that you need to know what you learn. Yeah. Okay. So that's why we need reasoning for several how to say applications. We will also need reasoning and not just machine learning. That's what I believe. So what is reasoning? What is my view of it? You have a database, you have data, factual data, and you have knowledge represented in form of rules, and this knowledge produces new data. Now, this new data could be just produced ad hoc when it is needed, or it could be stored in an extended extensional data, in an extended database, yeah, where you have all these red points, which actually are called intentional new facts, and you have here your old facts, which you call extensional facts, extensional database. Okay. Now, whether these red points are stored or whether you just produce them by need, when you need such a point, you do some reasoning and you establish this. This is application dependent. I will not now speak too much about this. So what do the rules here, and what do they encapsulate? They encapsulate many things, among which, for example, I mean, this is not limited to this, human experience, common sense, and expert knowledge just of the type that I have shown you just now, yeah, with the credit rating or with the other examples. Definitions, norms, laws, regulations. There are rules that we make. It's very difficult to say a machine learning program should learn a law or a rule, because we make, society makes this rule. Machine learning will not know this rule. We have to tell it in addition to some learned rules. These rules are rules that exist because we have made them. Yeah, they are not in nature and they are not in the data, and so they cannot be learned. And of course, also machine learning rules. Why not having rules, statistical rules that are learned from machine learning, from big data? Okay, so that's what I see as knowledge. So I don't exclude machine learning rules as knowledge. Knowledge is not just common sense knowledge. It can be generated by machine learning. Okay. Now here I will give you a very simple example. This example actually is for non-logicians, but it's such a nice example because it shows you how a single rule can make a database very, very, very clever. Yeah, it can introduce a huge quantum leap of cleverness to a database. Yeah. So here you have a marriage database, but let's say this database is in 10 years ahead. We are forbidden to say whether somebody is a man, woman, yeah, and now already 2 men can marry and men can marry women, etc. But now we still record it, but in 10 years this is no longer recorded. So we have here a database, yeah, where couples are put, but we don't know their gender. It could even happen now if you mix different marriage databases. In one, the male is first, and the other one, the wife is first. So one is the husband is first, etc. So this is a database, yeah, which doesn't reflect the gender, and which, in some sense, just puts for each married couple, it puts one tuple. Okay, for each couple, a tuple. It's very easy to remember. And now you see that some people like David Neven has been married twice. Neven, we know, is male, but here Taylor is in the same. Taylor is the same argument. Liz Taylor has been married 7 times, and here you see the intervals when these people have been married. Okay, and now you can ask the following query: when was Taylor married to Burton? Okay, and this database will tell you, well, you see Taylor Fisher, Taylor Burton. Indeed, these 2 intervals, because they divorced and then remarried a year later. Okay, so the answer to this query would be these 2 intervals, 64 to 74 and 75 to 76. Okay, but if I ask when was Burton married to Taylor, the answer would be empty, because in relational databases, I have an order here, and there's no tuple that says Burton Taylor XY. Yeah, okay, so this is of course not good. But now, if I add the single rule, and here these rules are universally quantified here. So the entire rule is for each u, v, x, y. If u is married to v during the interval x, y, then v is married to u for the interval x, y. Okay? That's a rule. This is a typical a very simple Datalog rule in the language Datalog. Okay, it's a logical rule. It's a horn clause, if you want. A universally quantified horn clause, a very simple one because it has no conjunction. It has just a single argument in its rule body, and yeah, It has also here a single fact in its head, which we usually will only consider, but we can also have several facts if we wanted. But for simplicity, we mostly consider languages with simple facts here. Okay, so that's a very simple rule. If we take this rule together with the database, and if we have a logical view on it and say, well, now tell us everything that follows. So query answering now means all the things that certainly follow from the database and plus this rule, then of course we can get the right answer, because thanks to this rule, we can infer that also Taylor was married from Burton during these two intervals, okay? So with a single, very, very simple rule, and there are of course much more complex examples where this is useful, but with a simple, extremely simple rule, we can make a database much more intelligent. That's what I want to say. So that's also an example that shows what is a rule, what is data, how rules can enhance data, okay? Now, we will not, if we want to do this and if we want to come to a point where rules are used really for reasoning over data and in a useful way, unfortunately, we have to look at stronger formalisms. And here I will only give you a glimpse of what has to be done. So we can use negation, classical and non-monotonic negation. Classical negation is here, for instance, if the weather in London at a certain date is rain, so you see all the attributes that are written with uppercase, that start with uppercase letters, are variables. So we would say for each date, if in London, so London is a constant, yeah, it rains on a certain date, it rains, it doesn't rain, sorry, it does not rain on a certain date. And if this date is a Sunday, okay, then there will be a park concert in Hyde Park at that date. Okay, that's a rule that I have actually seen a similar rule in some catalog. Yeah, on every Sunday when it doesn't rain, if it doesn't rain, then there is. So if we know that it doesn't rain, yeah, if it surely doesn't rain, yeah. Now you can also have other rules, and here's a typical rule that is very often considered in AI, yeah, which is has a different type of negation, which is called default negation. And there's an entire branch of AI that deals with these similar things. Let's say default negation, default reasoning, non-monotonic reasoning, non-monotonic negation. If X is a person and X is not known to be guilty, so if I write this not means not known to be guilty, then X is presumed innocent. Okay, so it's a different type of negation. Yeah, and even though I don't know that this person is guilty, as long as I know that I do not know that he or she is guilty, then he or she is innocent. But that's not all, that's just negation. And negation creates problems, yeah, because classical Horn rules are polynomially checkable, and you can do everything in polynomial time. As soon as you have higher types of negation, let's say, it becomes difficult. So there are types of negation where it's still polynomial. So a lot of research has gone into this, but that's not enough, unfortunately. Now we also have probabilistic reasoning, and I already spoke about this. In our example, we can say, well, if I move into a newly bought house, probably with very high probability, the previous owner went out, but I cannot be sure because maybe my auntie already was the previous owner, yeah, and still lives in. Okay, so we need to assess to be able to attach probabilities to facts. If the weather in London at some date, yeah. No, this is a fact here, and that's a rule. So the fact says on the 22nd, 12th, 1919, in London, will be heavy snow with 0.I. So that's a weather prediction, basically. Yeah, weather. Yeah, and then you have a rule with 0.3 probability. If the weather in London at some date, if there's heavy snow, then if there's a flight from London at this date, then the flight will be delayed. Yeah. So in 30% of the cases when there's heavy snow, flights are delayed. Yeah. So that's a rough rule. Yeah. I don't say how much the flight is delayed, etc. You can make a fuzzy curve or whatever. Yeah. But this is a reasonable rule. No, you have to calculate with delays, and that's a useful rule, because if you're doing planning in an airport, you need to have such a rule. And the people who do this currently still people, and it's not all automated. It's not yet all automated. Yeah. They use such rules, okay, either implicitly or explicitly. Next difficulty, which again is difficult to deal with, is disjunction. If X is a staff member, then X is a consultant or an employee. Next difficulty, existential rules, but very important. if there's a machine M of type T64 in a certain room, then there must exist a plug P in this room, which is a higher current plug. Okay, so there must exist some plug in this room. Okay, so sometimes we need even existential quantifiers, and the entire M and room is universally quantified. We don't just write these universal quantifiers because but we do write the existential quantifiers if they we could also say every variable in the rule head which is not already doesn't appear in the body is existentially quantified, but it's better to write the existential quantifiers because otherwise it could lead to confusion. And now we're coming to even more complex types of rules: recursion, arithmetic, aggregate functions, etc. These are all rules that are used for a lot of practical applications. And here's a rule that we really use in an application of a company that we created. We use this rule. It's a banking rule, okay? And the rules checks whether company X controls a company Y. And the rule in language, in natural language, is company X controls company Y. If either X equals Y, well, every company controls itself, or if X controls a set of companies that jointly hold over 50% of Y. Okay, yeah. So then we can say, let's say, it's better to see that this is owns XX. Okay, X owns X. Yeah, but we can also X owns X. Let's say it owns. Here we should have owns. Then we say controls X, Y, and owns Y, Z, W. Okay. So what does owns Y, Z, W mean? Y, Z, W means the company Y owns another company Z, a third company Z, with owns a proportion W of this company Z. So 0.5 if it owns 50%, for instance. So this W would be 0.5. And then we compute the sum over all such Y's, of the W's. And if this is greater than 0.5, then X controls Z. Okay, X controls Z. So I make here a slight correction. That should probably be, it's safer here to say, every time I make this error and forget to correct it, that this is owns, every company owns itself. This could also be in the graph. Now you have a bit, but this is just reflects these rules. What does it mean, company ownership? Control. What does control mean? Control means you own more than 50%, but not necessarily directly, but through a chain of other companies. And that's what fraudsters use very often. They construct a big network of companies so that they, in a certain sense, hide the proper own control. That a mafioso, for instance, a mafia boss controls another company. And the central banks of each country, should actually find out if there are such hidden relationships, and especially if a company asks for a loan. There's now a regulation in Basel III that you cannot give a loan to anybody who either controls you or to a loan cannot be guaranteed by another company that either owns you or that you own. Or that either controls you or that you control. So there are such kind of rules. This is actually a simplified rule, but I want to already show you that this is already a difficult rule. It has recursion, and at the same time it has aggregation, because it makes the sum of all this over all these Y's that match this, and the sum of this W over all matching Y's, and then it checks whether the sum is greater than 0.5. This becomes computationally even more onerous. Okay. Now, and also conceptually more difficult. Now, we have really applications in this area where we have more complicated rules for this: ownership, family relationship between companies, etc. And this is used for very, very big bank databases, with millions of companies. And so you have such a database where we basically, such a company database is a big graph where each company is a node, and where ownership is basically a label of an edge in this graph. Okay, and then you have to compute, if over a graph with millions of companies, you have to compute this. So this is really difficult to do. But here I just want to show you what we need to express. We need recursion, we need aggregation and things like that. Okay, so here you have the example again, but I think it's clear. So what automatically comes out of this is the question, well, reasoning is a complicated task. We know that in general reasoning is undecidable, but now it's even worse because now nowadays we have big data and very big data, millions and millions and millions of companies, social networks, etc. Yeah, and there's an enormous amount of research now on rule-based knowledge representation and reasoning. And what is really problematic in practice is the high complexity. I mean, this is where complexity really matters. You cannot do that with a SAT solver easily. Yeah, you can. SAT solver can give you sometimes good results, but it's not. Yeah, yeah. I'm not following Moshe's thing. MP is solved. Yeah, people cannot apply subsolvers in all such situations. Sometimes you need to have an exact result, etc., and a guaranteed result, and so on. So. In most cases, reasoning is either undecidable or it requires exponential time for most formalisms. And so my own research goal, and those of many other people, of course, over many years, was to find lightweight reasoning formalisms that work for big data and suit real problems. Yeah, so having low complexity, but maintaining the highest possible expressive power. And of course, that's a trade-off. Yeah, complexity and expressive power, but you can still engineer a lot. Yeah, that's the good thing. I mean, it is a trade-off, but there are some formalisms that are dumb and they have a high expressive power, and then there are some smarter formalisms in a certain sense, yeah, that are less complex and can be done in polynomial time under certain reasonable assumptions. Okay, so and this is what we have been doing in our basic research, and I will not go into many details here. Yeah, I could have other talks where I expand on this very much, but we are have been looking for languages, yeah, that have fulfill basically these two criteria: to have low complexity and possibly a high expressive power, but high expressive power with respect to what? With respect to real life problems, such as those problems that I have explained now. Problems that you really need in banks, that you need in credit rating agencies, etc. Okay. Now, we have classified several types of languages, and so we have, for instance, we have defined one language for which we have implemented a system that is the Vadalog language and system, and this Vadalog language is a kind of extension of Datalog with existential quantifiers, with stratified negation, so with a mild form of negation, but which is sufficient for most purposes, with the possibility of saying that something is false, so with the bottom sign in the rule head, which means false simply, and existential quantifiers already mentioned. And within this, so this fragment can be a fixed logic formula, can be evaluated over big data in polynomial time. Yeah, so this is the famous, what Moshe Vardi created as an idea. You cannot just look at the complexity of a system of input-output. You have to say, well, we have data, and then we have logical formulas or rules, a set of rules. Yeah, and normally the data is very variables, but the rules are small. The set of rules, I mean, the rules, there are not too many rules. The data is big, but the rules is reasonably small. Man-made, handmade, basically, yeah, and you can consider them to be fixed, and your query is also reasonably small if you have a query to this data, yeah. So what is really variable is the data, and so we call this, Moshe called this data complexity, and we use this because this has turned out to be a really good notion for assessing the complexity of a formalism. So basically to distinguish between the data part and the rule or formula, or logical formula, or theory part, if you want, and to say it's the theory, the rules are fixed, but the data are variable. Okay, so there's a lot of basic research here in order to establish this mathematical logic, finite model theory, computational complexity theory. You have to really understand complexity classes and to find fragments that fit into, for instance, this n-log space, which is a very good complexity class, or even smaller complexity classes like AC0, which is the complexity of fixed first order logic formulas. Yeah, and then this would exclude recursion, for instance. Okay, and then there's also a lot of software engineering research to how to implement such systems. Okay, now let me just explain which kind of rules we are interested in. on one example. So we are interested, for instance, to be our formalism should also englobe or incorporate what is called description logics or ontological reasoning. So here you have this formula is written in description logic, and this means this formula here can be expressed in first order logic as follows. For each x, if x is a professor, then there must be at least one student to which x teaches. Okay, not always true, by the way. Yeah, but let's assume it. The university will fire this professor if he teaches to 0 students. Then for each, this is also a rule that is not always true, but let's assume it's true. Either person is a professor or a student, that we can express this with the so-called falsum or the bottom sign here. Professor X and student X implies false. Okay. Then we can say there are other rules, for instance, the symmetry rule. There has tutor minus included in teachers too. That's how it's written in description logics. Yeah, this is a different formalism. Syntactically, it's very strange to me, but it is equivalent to say for each xy, has tutor xy implies teachers to yx. By the way, this syntax is not so bad because description logic is a kind of modal logic, and so they want to avoid variables. But I'm much more a friend of Datalog like, and I prefer actually this, but I understand there's a reason also to avoid the use of variables here, because then you can really show it's a kind of modal logic. But I can say, well, in a similar way, we can show that this logic is actually a guarded logic. Okay, this is not guarded. This is also guarded in this specific case, but yeah, this is a guarded logic here. Yeah, and modal is part of guarded. So why don't we just use guarded? Then yeah, we're fine. But it turned out that guarded is not enough, and that's why we did a lot of further research. And then we have to a limited number also of rules, to a limited amount, we allow rules of this form. Has tutor xy and has tutor xc implies y equals c. So this is a functional dependency. Yeah, it's known to be a functional dependency. Now we know that again from Moshe Wadi, who built the fundamentals of this, and from other people too. I think Moshe and somebody else showed that functional dependency and these types of rules, yeah, which can be called inclusion dependencies, that they are already undecidable. Yeah, but if you limit the use of this, yeah, then in a precise way, then you can still have in many reasonable cases these equalities. Okay. So again, this is a picture of what we are studying here, and we are studying the data complexity. And there's a lot of interesting work to be done, and we are not finished with the formalisms. Okay, and we want to have, of course, logics that are not only polynomial, but also that are highly parallelizable. Because nowadays you want to send things to multiple computers, and there are several paradigms for this. And so n-log space turns out to be a good complexity class, and we have identified fragments of these good logics that are n-log space. So now I will give you, this is, I think, the only real technical, but it's also not very technical slide, but I don't have to excuse myself for this here, because you're a technical audience and I'm doing a non-technical talk. So that's what I have to excuse myself for. So what is the rules we are mostly interested as a basic formalism are so-called worded rules. And why do we use worded and not guarded? Because Datalog itself is not guarded. Okay, what we wanted to have is an extension of Datalog, because we think that Datalog rules, which are these rules that I showed you, the Datalog rules, yeah, are really important. That we want to have all Datalog, maybe not, certainly not for the n-log space fragment, but at least for the polynomial fragment, for the full language that we have, for the full basic language, we want to have full Datalog in it. Okay, so that's why we can't use guarded, because Datalog is not guarded. Yeah, Datalog has, in Datalog we would have a rule like P of xy and S of yz implies there exists a TYXW, for instance, and that's already not guarded. Yeah, because guarded means there's one atom that contains all variables of this rule body. Okay, so that's why we can't use guarded, because in practical applications, you very often, as long as you don't have to deal with existentials, yeah, with existentially created values, but yeah, just give a hint here. Yeah, you often want to do so-called joins, and you want to have in classical database operators which are not guarded. This is a join operator, yeah, in database terms. Now, how does worded work? Well, worded, in a program, we first identify where the so-called affected positions are. what are these affected positions? Affected positions are positions where possibly for some database, let's say, yeah, an existentially quantified variable can come in. So certainly, if we start here in this rule, well, here exists W, so the third position of T, yeah, will be affected. Okay, so therefore it will also be affected here, because once the third position of a predicate is affected, it's affected. So it's affected everywhere. Yeah, it means there could be some mix-up with existentials. And given that we will, and I will not go into detail, we use algorithms like the chase, etc., yeah, that plug in null values, specific Skolem constants for existentials. Yeah, so that means Skolem constants can come in here. Okay, and therefore they can come in here. Okay, if I can generate something where here there's a Skolem, they come in everywhere where we have T. In the third position we can. So we determine basically by a very simple recursive process that just analyzes the program and no data. Yeah, we determine where existentials can come in, and these are the affected positions. Okay. And then we define what a dangerous variable is. What is a dangerous variable? A dangerous variable is a variable that occurs in a rule head, okay, like X, and that occurs in a rule body only at affected positions. If it also occurred at a non-affected position, yeah, then by the non-affected position, it would be bound to contain no Skolem functions. Okay, so that would be good. But if it's only in affected position, so that's a problem. Yeah. Okay. So dangerous variable. This is a dangerous variable. This X. Yeah, because it occurs in the rule head. Yeah. And it occurs in the rule body, but in the rule body, it occurs only in affected positions. Okay. Now, why isn't the Y a dangerous variable? Then why isn't this position here where you have this Y a dangerous position? Because this Y occurs in the rule head, and it also occurs here at an affected position, but it occurs at an unaffected position. So that means there could never be a Skolem function in. The Skolem function cannot come in, cannot mingle with this position, basically, yeah? Because, of course, the possible elements that can occur here are the intersection of this and this, and given that here there is no Skolem function, yeah, no Skolem function will ever come here, will be considered here, it will be, yeah, to make this body true, okay? So that's the reason. Now we can say, if all dangerous variables jointly occur in a single word atom, yeah, like here, all dangerous variables here and here occur in a single atom of the rule body, not in two atoms, okay, or three atoms, in single atoms. Dangerous variable, there should be for each rule a rule body where the dangerous variables occur there should be a single atom for each rule body that contains all dangerous variables, only the dangerous ones, yeah. And this is called the word atom. And this word shares only unaffected variables with the other body atoms. So in fact, these variables counts as unaffected because, yeah, it here appears in an unaffected position, and so that counts for us as unaffected. Okay, so this is good, no problem. Well, here there are no other no other elements, so that's all. That's trivially, yeah, vacuously fulfilled this second condition here. Yeah, so this is how our logic looks like. Now it looks a little bit complicated, but it's not very complicated. And what we noticed is that actually there are benchmarks. There are lots of benchmarks for existential rules in the literature, and each single rule in these benchmarks, yeah, a program in this benchmark, yeah, has rules in our language. So the language covers all benchmarks. We haven't found one benchmark. We have found a benchmark that can be one single, I think, that can be rewritten. Yeah, that has to be rewritten in this form. Yeah, okay. But at least every benchmark you can rewrite it that we have looked at. Yeah, you can rewrite it. And of course, also these rules here are all. This rule here trivially it has only one atom, so everything occurs here, and every dangerous variable, it has a dangerous variable Y, but it doesn't occur here, so no problem. Yeah. So this rule is worded. This rule here doesn't have to be worded. The rules with the constraints, they don't have to be worded because they are just you can manage them by just issuing a query whether this is true. Okay, so these rules don't have to be worded in the worded Datalog program, and this rule is also worded. It has only, you know, these rules are very simple, so they are trivially worded, but you can see this rule doesn't have dangerous, doesn't have an existential quantifier, so no problem. Yeah. Okay. So this is a new concept basically, but the good thing is now, as opposed to guarded, yeah, to guarded Datalog or guarded extended Datalog with existential quantifiers, now this contains full Datalog, even unguarded rules, because as long as I have Datalog, as long as I don't have an existential quantifier, everything is worded. Every Datalog program is a worded program. Okay. Okay. So these are the words, and that's it. And I just want to say, but we have a lot of theoretical results on this, because then you want to extend this by other things. Now we are working on probability right now. Yeah. So we can, of course, manage to a certain point, we can manage it, but not to a satisfactory point. And we want to have a satisfactory interpretation of, it's still polynomial interpretation of probability. That's what we work the next term, basically. We have started already to work, but we have a seminar that exactly deals with this in Oxford. And we have already built a system that can do things and that we are continually improving. And basically this system is a kind of knowledge graph management system. It uses core reasoning, it uses reasoning in the core, and then it attaches to so many databases, machine learning in a very simple way, I have to say. Yeah, we don't have a sophisticated mechanism how this attaches to machine learning. Basically, by interaction, you send something to a machine learning program, the program classifies and sends it back, or you could also bind some predicate, some classifier predicate, and every time this predicate is asked, so it's just syntactic sugar, I would say. On the fly, it performs some machine learning task, and then you could also integrate learned rules. That's already more difficult, and we don't have a. So this is what we are doing now, and this is what we are working on: how to integrate machine learning, yeah, how to combine rules, and I will come back to it. Machine learned rules with human-made rules, okay, with expert rules. Nobody. There's very little research on that actually. How to combine them really, yeah, not just how to help machine learning with expert rules, but imagine you get rules from these two different sources, how to combine them. And again, here also learned rules, but with a different type of interaction, direct interaction with the machine learning process. I will not go into the detail. I will say, so we have already mentioned there was tremendous progress, recent progress in machine learning, in particular deep learning, reinforcement learning. We mentioned it. New data analysis techniques. And unfortunately, logical reasoning techniques have lagged behind. Yeah, mainly because, and I say it's not because we are such idiots and the machine learners are so good. Yeah, that's what they think. Yeah, not all, but most of them, many of them. That's many. Yeah, okay. Of course, there are a lot of people who are come now from logic. Martin Grohe, I have seen, is here. He combines this in a very smart way. But many machine learners think, and even Hinton, yeah, has said, I don't think that he is still of this opinion, but until recently he said, well, let machine learning do everything. We don't need logic at all. I think that's wrong. Yeah, and this comes from the long suffering period that thing, and now the sudden, yeah, you always need to digest, let's say, a sudden huge success, and machine learners have not really digested it yet. Okay, we were in the same boat, in a similar boats, in two twin boats, let's say, in a catamaran. Yeah, we were a catamaran, and unfortunately, one part of the catamaran is lagging behind, and the other part is so happy about it. Yeah, that's what I'm sad about it. But anyway, we can't do anything. Yeah, but I don't want to get sentimental here. However, many now more and more researchers, even in the machine learning community, believe combining machine learning with transferable knowledge and logical reasoning is essential for achieving the next level of AI. And for instance, Gary Marcus says, we urgently need to get cracking on building machines equipped with common sense, cognitive models, and powerful tools for reasoning. Together with machine learning, these can lead to deep understanding, itself a prerequisite for building machines that can reliably anticipate and evaluate the consequences of their actions. That's also important. Evaluate the consequences of one's action. A machine should do that too. The royal road to better AI is through AI that genuinely understands the world. Yeah, so this is exactly what my proposal to the Royal Society, I have now a 5 years project, is about. And I want to give you an analogy, the brain lateralization thesis. Now, this is all known to you. The brain lateralization thesis says the left hemisphere specializes more in verbal and language skills, and the right hemisphere specializes in visual and spatial activities. Now, this has not been really proven, but I think most neurophysiologists believe, again, I say not every, most, 99%, believe that there is a lot of truth here. So I went in Vienna to a ball, to the science ball in Vienna. That's a very nice, beautiful ball that I can recommend to everybody. It's a ball where you don't have to necessarily to have black tie or a tux. You can also go with a normal jacket, and even without a jacket if you want. I went with a normal jacket and tie, not with a tux. But what is really nice is that all scientific groups, yeah, from Vienna and from Austria and many international people now meet there. They have it as a meeting place. And so I wanted to know, what are people now thinking about the brain lateralization thesis? So I went to this ball and I asked, so where are the neurologists sitting? Where are the neurophysiologists sitting? And then I identified two tables where they were sitting at about 10. And then I could broadcast it. Can say, so guys, sorry, the music is very loud. I have to shout, but what do you think about the lateralization thesis? Then basically the result was, yes, there's a lot of truth to it, but there's a lot going on between the two hemispheres. Okay, and that's very interesting, because that's what's going on, is what you have to do to combine machine learning with rule-based knowledge. My vision, my naive picture in my brain, how it looks like is that on the left part of the brain, yeah, we have kind of rule-based knowledge, and this rule-based knowledge take their arguments, the rules take their arguments from things that we recognize, from facts that we recognize in the right part. And of course, it gets more complicated because the right part learns in continuation, so it can learn such a rule also. Yeah? First of all, it was a given rule. It can then immediately learn an association between X, Y, and Z, etc. But in the most primitive case, that's how I imagine it works. Of course, this is not science, yeah, but of course, if we want to simulate something, that would be a nice way to say, okay, we have rules, but these facts are machine learned. But that's probably too simplistic, but I think it's a nice picture. Yeah. So in practice, recognition, as I already said, is the main task, that we recognize objects. Yeah. Oh, a fly agaric. This is a poisonous mushroom. Yeah. But so this woman recognizes a fly agaric, but her grandma told her fly agarics are poisonous mushrooms, and if you eat poisonous mushrooms, you may die. So 2 rules actually, yeah, and you use these 2 rules, okay. But of course, if you do it twice, for the first, third, and second time, when you look at the fly agaric, you will reason and remember what your grandma told you. But then if you say it, oh, poisonous, yeah. So that's why it is not so linear, because the right part of the brain also learns what has been learns to do deduction much faster than the deduction itself. That's what I want to say. Okay. Again, it's my theory, but there is already some evidence and some support for it. Yeah. So the right part of the brain would be induction, self-learning, intuition, what a baby is doing, what animals can do. The left part of the brain, deduction, transferable, and verbal knowledge. The right part more corresponds to neural network statistical learning. The left part more to expert system, knowledge-based system. The right part computationally very fast, highly parallelizable. Another interesting thing, neural networks are very fast, okay? Very fast, because they are parallel structures. They are not very deep in general. Yeah? Even if they are deep, they are polynomially deep. Usually they are logarithmic, even lower, yeah? Few levels, yeah? And therefore they can very fastly compute the result. And we know, unfortunately, that reasoning is, at least in general, NP hard. That's why we are constructing polynomial logics that are equal, that are also good, but sometimes we will also have to deal with NP hard problems. And our philosophy will be to outsource them to an NP solver. And that's why in our Vadalog system, we want to make an interface also to an NP, to constrain NP to solvers, SAT solvers or other solvers that can solve NP hard problems, yeah, like logic programming with negation, with stable negation, etc. Now, and if you now look to Daniel Kahneman's book, thinking fast and slow. That perfectly fits this. But the interesting thing is this fast has now also another hardware meaning. Basically, a neural network can really reason fast, and logic is really so terribly slow due to this NP problem. Okay, good. The key idea for the first key idea, I say a first key idea for bridging the two types of AI could be, and that's what we want to do first in our project, to look at expert rules taught, transferable knowledge, common sense knowledge, domain knowledge from textbook, laws, human experts, and on the other side, machine-generated knowledge, yeah, that could come from data mining, for instance. Data mining is a kind of machine learning, a very simple form of machine learning, but also for machine learning, you can extract rules from machine learning. Yeah, there are thousands of papers now that say how to extract rules from neural networks. So this is already possible. Maybe it could be improved, but it's possible. So now you have these two types of facts and rules that are machine learned facts and rules, and you have expert knowledge that you superimpose to it, or the other way around. Yeah, and now very few people have studied the interaction mechanisms between these two objects, between these two types of knowledge or whatever. Yeah, rules, between facts and rules. Yeah, so that's what we want to study first. But that doesn't mean there could be certainly a tighter interaction. We can directly work on the data with rules and submit this to machine learning, etc. So that's not, yeah, but even this is a very interesting problem, and that's a problem where we start with. And another first step would be to define a control theory for machine learning. So what is control theory? We all know what control theory is. It's the old theory of controlling a process. If the process goes beyond its boundary, we stop, we bring it back to its boundaries, for instance, by switching off a heater. Yeah, if the temperature gets too high, we switch it off, and then it goes again down. And if it is too low, we switch it on again, and so on. And so we keep it into these boundaries. And there could be, let's say, a logical process where machine learning learns things, maybe things that are not correct, or maybe things that are forbidden that it should not learn. Yeah, and then we match this with rules. So we check for logical consistency with rules, and then we interact again with either with the data or with the machine learning process. So that in a certain sense that we have a kind of feedback loop, but we don't know exactly yet how it should look like. But I think it's very tempting to say a very loosely coupled way of combining machine learning with rules is akin control theory, and could actually, logic could act as a control instance for machine learning in a certain sense. Yeah, but what is learned doesn't fit. There must be something, and then it will be analyzed, and we change either the data, or we change the machine learning process, or we just suppress a result if this is unethical, for instance. Yeah. So what our project, however, what we want to deliver in our project, a new rule language. We already have Vadalog, but we need to improve it, especially with a better form of probabilistic reasoning. And then theoretical foundation of rule interaction, new reasoning methods of algorithms that take into account machine learning and logic, a software toolbox, etc. Question, yeah, is the combination of machine learning and logical rules feasible in useful contexts? Yeah, achieving these goals that I just mentioned would contribute very much towards the next level of AI, combining machine learning with transferable knowledge. But is it feasible? Will I be able, or will we be able to achieve it? I mean, I think that's a great research challenge. I'm very optimistic, and that's why I want that's with what I want to finish my talk. I'm very optimistic because we have done a system where this was done more or less ad hoc, where we more or less used rules and machine learning in combination ad hoc. And this system is called the Diadem system. And this system was used to extract data from web pages, and we just had to give web pages in a certain domain. So for instance, in real estate, or in used cars, or in hotels, or in restaurants. So for each application domain, real estate, cars, etc., we wrote a different knowledge base of rules, and then we wrote a system that can take the knowledge base, that can also machine learn, yeah, what is an address in this context, etc. yeah, combining these rules, but in a very ad hoc way, I have to say. So not in 100. So the combination of machine learning and logic was not done in an extremely principled way, but still, yeah. And this system was used, or is currently used. It was bought after by a company called Meltwater. And Meltwater uses this as their main system for extracting data from the web, and is very successful with it. I'm very proud about this. And this system therefore combines machine learning with rule-based reasoning. In production, it extracts from now more than, that was, this slide is a little bit older, more than 200,000 websites in parallel, from various application domains. It extracts data, and it's successful in more than 95% on the test sites. And now it has been improved. It has been sold to Meltwater in 2016. In the meantime, all these results have been dramatically improved. Now, what kind of rule-based reasoning do we need for data extraction? We have ontological rules. I already spoke about, but gave you some examples. But here, a typical ontological rules in the domain of a real estate is: a flat is a real estate property, a house is a real estate property, a real estate property has a number of rooms, a price consists of a number and the currency, etc., etc. So this is a rule that can be used in several contexts, of course. So this is a reusable rules, but these rules are not reusable for cars, for instance. Okay. Then we have other rules that we discovered, another type of rules that I call phenomenological rules. Phenomenology means how do entities manifest? It's the science of manifestations, yeah, of the spirit of things, etc. But in this case, I mean, how do entities manifest themselves on the web? So for instance, a phenomenological rule would be the text chunk closest to an input field is with high probability its descriptor. So if you have a web page and you have a field that you have to fill in, where you have to put a minimum price, yeah, this is an input field, and then below that field it writes min price. So this min price is the descriptor. But of course, a program doesn't know it, yeah. We know this. This is a general rule that we know. That could be machine learned, but we already know it. So why don't we just use this rule, yeah, in order to recognize and to label what an entity on a web page is. Oh, this entity is the descriptor for this other entity, and the other entity being an input field, okay? Or each sales item is described in a convex, usually rectangular region. That's very important. If you look at the price table or the description table of houses, you have several houses depicted on a web page. Yeah, how should the computer know that this price doesn't belong to this house? Yeah, but that this price belongs to this house. Okay, so this is some knowledge that you can give, which improves, yeah, the capacity of the computer to, of course, also this could be learned, but it's so obvious that it's easier to give it to the system than to learn it. And then we have a lot of rules that cannot be easily learned, okay? Then we have, for instance, this is not easy to learn, site exploration rules. Before filling a field, try to leave it empty, yeah? If I want to have all properties sold by a real estate agent, as it's called in England, by a realtor, yeah, all properties sold by a realtor, yeah. Why would I put a minimum or maximum price? I just leave the price field empty, yeah. That's a typical human knowledge. Machine learning would have a hard time to discover this because it doesn't know that it has to discover such things. Yeah, this is now action. Of course, yeah, this could be reinforcement learning and exploration. But this is, before we do that, I mean, should we learn all these things before we can have a usable system? No, we already have knowledge. We don't want the computer to learn, for instance, all mathematics and physics. Yeah, we have this. Learning this, I'm not sure if that's possible, probably not. Yeah, it would take 100 years to learn, or maybe it would take 20 years for a super learning program to learn a lot of mathematics, but we already have it. We have our formulas. So that's our knowledge that we want to incorporate into the system. Yeah, rules for handling next page links, etc., other types of rules. And now I want to finish this talk with a very short demo of how our system works. Let me see if you can see it. Please let me know if you can see it. Can you see the picture? Stefan, yes. Can you?
Yes.
Okay, very good. So what you see here, we have made some annotation for this. This is actually a movie that is taken from the system, and these boxes, we have superimposed these boxes to give some explanation, okay? So here we have a list of thousands of URLs. These are all the real estate agencies, okay? That's the input to our system. nothing more. Okay, some of these links will not work, fine. Yeah, some of them will no longer, they may have been, now especially unfortunately many are bankrupt. Yeah, okay, yeah, that system will discover that there are no properties on it, or the web page doesn't work. This, where do we get this from? Well, we could have another program that looks for this, but usually you find this in the yellow pages, or you can buy it, etc. So that's not the problem to get to this list. The problem is to get the data from each of these websites, from each of these websites in a uniform way, so that you can put this data in structured form in a database. That's the problem, to discover, extract, and reformat this data in a correct way. Okay, so now this is the input to our system. Okay, now we launch the system on this input. It goes to the first web page. Okay, and as you already see, the system, what we have here is the different logic programming blocks, blocks of logical rules, etc. that the program launches. That's just for internal use, so that we know what is going on and what it has done. And of course, we also have things like visualize generator, etc. Filling generator. It has already detected that this is a sales toggle. This toggles between sales or lettings, and we classify this as by rent. Yeah, for us, this is by rent. On another web page, this could be called actually, what do you want to buy or rent? Yeah, okay. This field is bedroom number. This field is search button. Yeah, this field is property type. Okay, so our system has automatically classified this, and of course, it used the ontological knowledge. Yeah, that these descriptors here, that the original text, this text is now superimposed by our system, so that we know what was classified. But this was the original. This is the original text near the field. This text is the descriptor, and we also help this text helps our system to understand what this field is. Okay. Now let's go on. So it explores this page. It classifies the fields, and it tries to do it with the fewest queries, namely leaving the fields empty. Okay, and it clicks on this. Yeah. Okay, now it comes to special pages where we have several properties, and we also have next page links. So it has to understand all this. And here, as you see, it already classifies the relevant attributes. So of course, that we have to say to the system, which type of attributes of the single properties on the market do we want to extract? So it actually also extracts the text, as you see, and this text can then be submitted later on when it's already in the database to natural language processing. So that's the next step. That's not part really of data extraction, even though we can look for some keywords if you want. Yeah. So it has several. It recognizes this postcode. It recognizes the price and other entities, name of the property, etc., location. Okay, and it goes on. It does this. And as you see, it has also segmented the page. It has found the convex area where each object is described. So maybe now we have a good visualization of what I said before. Every description of a single object is inscribed in a convex area, okay? And the system looks for such convex areas, and that's called segmentation. Segmentation within a list, okay? Okay, now it goes to the second page, and the system learns, yeah, it learns exactly where. So we use also machine learning, but we use machine learning mostly for recognizing small entities here, okay? And then we have rules for connecting these small entities to big entities. Now it clicks from sales to lettings probably, or yeah, lettings, okay? And now it explores lettings and it does the same. It recognizes this, okay? And so here I have to show you now what the system produces. Our system, the Diadem system, first analyzes the page. And what you have seen is it analyzes a web page and tries to locate and to find the regularities. So it's a kind of machine learning, yeah? Find the regularities of where to find objects and how objects are structured. And now, once it has explored a few pages, this has 100 pages, it has explored only 3 pages, it generates a so-called wrapper. A wrapper is a program in a language, in a programming language. In this case, it's a language that we have actually defined, which is called XPath. For those who know XPath, it's a kind of extension of XPath by navigational facilities by navigational commands, etc. Yeah, like button, push button, etc. But we need to explore a web page. Yeah. Now, basically, this is a very fast program. The analysis process is not so fast, but once the program has understood, it just generates this program, and this program is now sent to the cloud, and on the cloud it will extract very fastly all the data from this web page, yeah, and we'll send it back to a central database, and that is done then in parallel for many hundreds of web pages with 100 cloud computers, and each computer, as soon as it finishes, takes another web page, and there's a dispatcher that sends web pages to the cloud. Okay, so that's how it works. Now, let's see how the program works on it. Yeah, so sorry, let's see what the program has extracted. Here you can see what this program extracts. Actually, this could be already, I don't remember, but this could be from several vendors already, from several realtors. Now here you see how it works on with another realtor. Okay. You also look inside this, because this gives you very good hints what these fields are. It classifies these fields and it tries to submit without filling, but the system fails. So here it notices, okay, if you fail, then try to fill, and try to fill with various things so that you understand. Try to fill with location, because here it has York, so maybe it puts London in, yeah, just to try. And once it notices this is a city that I had to fill, it will fill all cities. It has a database of cities, of course, yeah. And this is domain dependent, yeah. It fills this and finds this, etc. Yeah. And I don't have probably any more time. Do I have more time? Probably not. Professor Szeider, I cannot hear you.
Yeah, no, I have to unmute. Yeah, actually, we are already quite a bit over time.
Okay. So I have a similar example with used cars, but I will not display it. And I will just say thank you for your patience, and thank you for attending this. And I hope you liked it. And I'm ready to answer questions, if any. I'm not sure that I can answer all questions, because it's a huge engineering team was, did this system. So I will not answer all technical questions, but certainly some.